Alright, now as you already know, not all systems of linear equations have got solutions. You remember that you've got these situations where you might have parallel lines, and parallel lines, of course, never cross, so there is no solution. So in a matrix equation, which has got the form AX equals B, if our coefficient matrix A, is singular, you remember what the word singular means? It means that it has no inverse. That is to say that the determinant is equal to 0. If that is the situation, we have no inverse, well then the system represented by the matrix equation will not have a unique solution. It will not have exactly one point where all of our lines intersect. That means it will either be an inconsistent system with no solutions, or it will be a consistent dependent solution with infinitely many solutions. So let's try a matrix equation approach on this example here now. We'll try to solve a nice 2x2 system. It's nice because it's already written in standard forms. That saves us a step. So let's begin by writing it out as a matrix equation. And so I'll write my coefficient matrix, -3, +4, -6, +8. And this is going to be multiplying my variable matrix. X and Y are my variables in this case. And it equals my right-hand side, 318. Now I know that in order to get my x, y by itself, I need to pre-multiply both sides of the equation by the inverse of my coefficient matrix. You can see that I'm skipping a step. I didn't bother to demonstrate the pre-multiplication on the left-hand side because I know that these two matrices, as inverses of one another, are going to multiply out to give the identity, and the identity times anything is still going to be that same thing, and it will disappear. And so I'm going to pre-multiply both sides by the inverse. On the left-hand side, they've cancelled out to isolate my variables x and y. And so I just need to multiply these out. Alright, so here we go. I'm going to go into the matrix, and I'm going to edit matrix A. It's no longer a 3x3 matrix. I now have a 2x2 matrix. And so let's enter its values, -3, 4, -6, 8. And I also need to change matrix B into something that is now a 2x1 matrix. So I'll edit matrix B. It's now a 2x1 matrix whose values are 3 and 18. And now I'm ready to do the same calculation as I did last time, A inverse times B. By the way, there's a nice little feature on your calculator. If you ever want to do the same thing that you just did, we'll press second, enter, and that will bring up the last thing that you entered onto your calculator. You remember, of course, I've now updated my matrices A and B to be the matrices in this problem. Let's see what happens. Uh-oh. It tells us that we have a singular matrix. And of course, if you, well, I don't even know how to write that. Uh-oh. So if you have a look at our original coefficient matrix for a moment, and we calculated the determinant of it, -3, 4, -6, 8. You guys know how to do a 2x2 determinant. We'll take the product in this direction, -3 times 8, and we'll subtract the product in the other direction, 4 times -6. This gives us -24 minus plus 24, and that equals 0. And because you have a determinant equal to 0, it is a singular matrix. That is to say that our coefficient matrix does not have an inverse. The inverse does not exist. So it's impossible for us to pre-multiply both sides by this inverse that does not exist. What does this mean? It means that x and y, which I can write as coordinates if I like, does not have a unique solution. So there is no unique solution here for my variables x and y. Well, this means then that it's either an inconsistent system with no solutions, Or maybe it's a consistent dependent solution with infinitely many solutions. You can imagine that would be coinciding lines. So the question said to solve our matrix equation if possible. We know it's not possible, but we still need to classify the system. Unfortunately, we cannot look at the value of a determinant and immediately be able to classify the system. A determinant of 0 means that it's either no solutions or infinitely many solutions. How do we make a choice? Well, I'm afraid the only real way that we can do this is by graphing. And so our matrix equation method fails miserably if we get a determinant of 0. All we know is that it does not have a unique solution, but we're going to have to revert to either our graphing of lines technique or our algebraic techniques of substitution and elimination in order to classify the system. Now I'm going to choose a graphing technique here, so I'll take my original system and I'm just going to write it in slope-intercept form. So if I isolate the y in the first equation, I end up getting 3/4 x plus 3/4. And if I isolate the y in the second equation to put it into slope-intercept form, I will get 3/4 x plus 9/4. Now, of course, we can see that I've got parallel lines. No surprise, every time you have a determinant of 0, we have parallel lines. But in this case, we can see that our y-intercepts are different. So not only do our lines have the same slope, but they have different y-intercepts, and that implies that our two lines are going to be parallel. So a slope of 3/4 going through a y-intercept of 3/4, and a slope of 3/4 going through a y-intercept of 9/4. I've got parallel lines, and thanks to my graph, I can see that xy has no solutions. And the last little point before we finish, I've said this already, but matrix equations are a much more efficient method than elimination or substitution, or for that matter graphing, especially when you're solving large systems of equations. And for that matter, I would probably advise you to use the matrix equations as your method any time that you have a 3x3 system or larger. But it might not hurt, I suppose, just to check the value of the determinant of the coefficient matrix. Because if you get a determinant of 0, then you know you're going to have to choose a different solution method. Matrix equations will no longer work for you because they're not going to let you know whether you have no solutions or infinitely many solutions. So you'd have to do a graph or substitution or elimination if you had a determinant of 0. That's actually very, very rare when you have a large system of equations. It becomes increasingly unlikely to have a determinant of 0 if you have a 3x3 or a 4x4 or a 5x5 system. So certainly the larger the system gets, the less likely it is that you will have a singular matrix, and the more efficient it will be to solve the system using matrix equations. And if you want to try this out, why don't you yourself, as an exercise, set up for yourself a system of 5 equations with 5 unknowns. And then see how long it takes you to solve that system using substitution or elimination, your choice, and then see how long it takes you to solve it using matrix equations. And I think you will see that the power of the matrix equation solution method becomes more and more incredibly powerful the larger the system gets.